Hello.
Yeah.
Hi.
Hi, Ben. So let us start the third lecture of this conference, and it's a pleasure to introduce my friend, Professor Benjamin Ken from Hong Kong University. And let me tell a little bit about him. That he is one of the most prolific researchers that I've seen. He's just works all the time, and outside that, he is a wonderful speaker. So we have Ben here, even though you are online, but we are in the seminar hall. As you can see, we have integrated MSc, PhD students who are just joined. So they're just after. So I can tell the students that he's a wonderful speaker, and if you concentrate, you'll be able to get many things from his talk. And in fact, he guides undergraduates also, from undergraduate to PhD students to postdoc to junior researchers. So he's a really prolific researcher and a wonderful speaker. He works in number theory, in modular forms, and all kinds of number theory problems, especially in quadratic forms and other things. So I welcome Professor Benjamin Ken for delivering his talk today. Ben.
Okay, thank you very much for the introduction and also for having me and giving me the chance to speak here. I hope to say something interesting. So I'm really going to start from a fairly basic point of view. So an m-gonal number is just, you take a bunch of dots and you arrange them in the shape of a regular m-gon. So, you know, a triangular number, you make a triangle. For m equals 4, you make a square, this kind of thing, and you count the number of dots. And if you do this, sorry, I didn't make any pictures, but if you do this, you'll find the following formula. So, for example, triangular numbers, you have x squared plus x divided by 2. This famous result of described by Gauss. If you take 1 plus 2 plus 3 plus 4 and so on, up to 50, you get 50 times 50 plus 1 is 51 divided by 2, and you get the number of dots in a triangle. And more generally, you get this formula, Pm of x. So the x is the length, it's the number of dots across, and the m is the shape, right? So this is the m-gon. And if you do that, you'll find that it's this many dots is how many you have. And if you allow x to be an integer, so this formula, of course, only holds for x bigger than or equal to 0 because x is the length. But you could, of course, just generalize it by saying, okay, we just allow x to be a general integer. And these are called generalized m-gonal numbers. And the kind of question that I'm interested in is something like the following. Suppose we have 2 m-gonal numbers, or 3 m-gonal numbers, or 4 m-gonal numbers. How many do we need to represent every number? So every number is the sum of some of these numbers. So you can take, you know, is 5 squares enough? Is 7 triangles enough? This kind of thing to be able to write every number using different lengths. So the number of triangles or the number of squares that you need. So Fermat, back all the way in 1638, conjectured that if you have any number n, you only need at most m-gonal numbers. So the m is the same both for the number of these figures that you need and the shape of the figure. So this is what he conjectured. And this problem was actually open for quite some time. Lagrange in the 1770 showed that this was true for m equals 4. This is a famous theorem of Lagrange called Lagrange's 4 squares theorem. So every number is the sum of 4 squares. And then Gauss and Legendre sort of separately and independently proved the theorem for m equals 3. So Gauss called this the Eureka theorem. So he wrote Eureka, triangle plus triangle plus triangle equals n. So it's commonly called the Eureka theorem now. And then finally, the general result was proven by Cauchy about 30 years later, so in the early 19th century. So we know that in general, you can write every number as the sum of at most m-gonal numbers. Okay, so this is this result. And let's think about the following generalization of this. Let's allow some of them to be forced to be repeated. So for instance, maybe you have to have 3 times the same number showing up. So if you pick some numbers, say alpha 1 up to alpha L, these are like the number of repeats. So the m-gonal number, Pm of xj, will show up alpha j times. So for example, if I do 1, 1, 2, then the first one would show up one time, the second one would show up one time, and the third one would show up twice. So I only have 3 distinct m-gonal numbers, but I have 4 total m-gonal numbers because the last one is repeated twice. So this is the kind of sum that I'm looking at. And I want to ask the same type of question. Can we classify all the n for which this what we call a Diophantine equation is solvable? So we want to know, is there a solution with x, for instance, in the integers, or in the natural numbers, or the non-negative integers, this kind of thing. So this is the kind of question that we would like to solve. Obviously, if we do it in the reals, it's a fairly easy question. So we do it in a restricted set like the integers, something like what we call a lattice. Now, if you start with this question and you complete the square, you get the following formula. Okay, so this might look like a bit of a mess, but essentially equaling n here is the same as some sum of squares. This thing here is being squared, and it's repeated alpha j times. And instead of n, we have some multiple of n plus sort of a shift. And that shift is exactly what you need to complete the square. So basically, this question about these kinds of questions with sums of m-gonal numbers is equivalent to questions about sums of squares, but with the added condition that we have some congruence conditions, right? So if I call this x j that times 2m minus 2 plus 4 minus m, if I call that y, then yj, then this is yj squared, but yj has a special property because the xj is an integer, so the yj has to be congruent to 4 minus m times this. And obviously, it will be, if we take xj to be an integer, we'll get all the possible congruences, ones that are congruent to 4 minus m. But if we assume that xj is non-negative, we'll only have some of the things in that, right? We'll only have one direction, so to say. We'll only have the positive direction of those. So another way to think about this is to think about it like a lattice. So a lattice is just a bunch of points spread out in space. And you can think of this q function as like the distance squared. So if all of the alpha j's are 1, then this is just the sum of squares. And the sum of squares is just the distance from 0. Right? So we have this idea of distance, and then you can think of the alpha j's as kind of dilating, pulling in one direction, right? So if you move in the y1 direction, it moves more quickly if alpha 1 is very large, right? So you don't have to move very much to go very far in that direction. And the question that we're looking at before about something equaling n, and now it's equaling this other thing, is counting the number of points that lie on sort of, if you think of it as a distance, you have the circle, right, is a fixed radius from 0. And so essentially you're counting the number of points on the circle. But because we've dilated, we've pulled in certain dimensions, we've pulled them, we no longer have a circle, we have an ellipsoid. So we've sort of stretched out the circle in certain directions. Okay. And the generalized polygonal numbers, these generalized sums, so if xj goes through all the integers, it just gives the counting of the points on the shifted lattice of, say, distance square root of n with that stretched sort of distance. So not necessarily Euclidean, but some kind of distance function. And you can write down explicitly what kind of lattice you have, because these are in the integers, and then you get 2m minus 2 times the integers plus m minus 4. So that's exactly where this is coming from. But with the yj's are in here, and then we have this distance defined that way. So as I said, classical polygonal sums, we're restricting now the xj's to be non-negative or positive. Well, this will just give one quadrant, right? if you have, so for instance, if you think of two-dimensional space, if L is 2, this will be one of the 4 quadrants. It'll be the sort of positive in both directions quadrant. The X here is a vector, and you're assuming that it's positive in every direction because you're taking n to the L, so it's exactly going to be that one quadrant. Now, if m is 4, there's a symmetry here, right? If I take xj to minus xj, there's a symmetry. And so taking non-negative, so if I allow 0, for instance, here instead of just positive, taking non-negative, if I multiply by -1, of course, I didn't actually change anything, right? If there was a solution with the integers, there's a solution with the natural numbers because of this symmetry. So if I have a negative solution, I can just change xj to minus xj. And similarly, if m is 3, I can take xj to minus xj minus 1, and this gives another symmetry. So again, I get, from one solution, I get another one. So for these two cases, m equals 3 and m equals 4, the two questions about solving this equation with xj non-negative or with xj in the integers is actually equivalent. But unfortunately, that doesn't extend beyond there because in general, we don't have this symmetry. So think about taking a lattice and you shift it a little bit. So take the integers and you shift them. If you shift them by an integer, then of course you still have the integers. If you shift by half of an integer, then you have a symmetry around 0. But if you shift by a third, you do not have a symmetry around 0 anymore. So essentially the m equals 4 is not shifting at all. The m equals 3 is shifting by a half. And then any of the other shifts will not give this kind of symmetry anymore. But you still might guess that it's almost symmetrical, right? The number of solutions in one quadrant you would think is probably going to be about the same as each of the other quadrants. Now, how many quadrants are there? Well, there's 2 to the L quadrants, right? You have all the possible directions of the xj's being either positive or negative. Of course, there's also 0, but somehow that's a much smaller set, right? So let's just ignore that for the moment, whether we're double counting the xj being 0 or not is actually not a very significant difference when we talk about saying roughly the number of solutions. So by roughly, I'm saying sort of asymptotically. So you might guess that this is indeed going to be about 1 over 2 to the L. So let's allow 0 just for simplicity, and let's take the number of solutions to this equation. Allowing 0 just means that we have at most this many xj's, so at most this many m-Gonal numbers. So if you can do it with less m-Gonal numbers, then it still is true. And then here I'm going to put a star for whenever I allow over the integers. So these ones where I have the full sort of lattice shifted in this space. And what we kind of expect is that the number of solutions with this restriction, that it's non-negative. So the question, basically the generalization of the question of Fermat, where he looked at these regular sort of m-Gonal numbers that have a physical interpretation, remember, right? They look like triangles and squares and pentagons and this sort of thing. So figurate numbers. So these m-Gonal numbers should be about 1 over 2 to the L times the number of solutions over the integers. And that actually is what we proved that I'm talking about today. This is joint work with Katrin Bringman and Minju Zhang. And we proved that for m equals 4, that this kind of guess is correct. So whenever you have an m-Gonal sum with 4 variables, so the alpha j has 4 different things in it, then essentially solving the problem of whether it's solvable with non-negative integers and solving the problem when you have all integers is almost the same up to an error, and the error is in some sense small. So we get n to the 15 over 16 plus epsilon, I should say that what's important is that this number is less than 1. So as n gets larger and larger, so as you go further away from the origin, this approximate should become more and more true, right? Because for small numbers, it might not be true, right? Because so essentially, if you have a small error, if the numbers are all small, then you can't tell a small error from the original value. But if you're very far away, then these numbers should be large enough that they start to look the same, even though there's some error, right? So you can think of this as sort of an expected value and the error from the expected value is one way to think about it. And this will be roughly like linear-ish around. There's some complications, but basically you expect this to be about linear, so that's why it has to be smaller than 1 here. Otherwise, the error will be larger than the main term, and then you can't say anything. Okay, so this is the kind of question that we're talking about. Oh, sorry, this should be the sum of squares here. I don't apparently have that. So here, I want to say that we have the xj's are congruent to R mod m, and the sum of the alpha j's xj squared, so just like this one, equals n. So this is the kind of formula that I'm going to look at. And by this relationship, I know that sums of this type with m-gonal sums and sums of squares are related as long as I add some congruence conditions. And so solving this kind of problem, finding the number of solutions to this kind of equation, is equivalent to finding the solutions to, again, sorry, there's a typo here. I'm missing the sum, missing the important part. The sum of the alpha j, so the alpha j again times xj squared should be equal to n. And so after completing the square, like I just showed you on the earlier slide, this theorem that we wrote down is equivalent to showing the same statement for sums of squares with congruence conditions. So we're going to look at sums of squares, so the S is standing for squares here, and we're going to look at the same question that we were looking at with m-gonal sums. And we're going to show that the error is small when we compare them in this way. Okay, and the basic approach is the following. We're going to use what's called a generating function. I know there's a wide variety of background out there, so some people have less and some people have more experience, so I'll just quickly review the idea here. So basically, we have a bunch of numbers, right? We have these numbers that we're counting something. And what we do is we package them all together into a function. So this is a function with some variable tau. And we're going to package it all together by taking a sum over all the n's. We're running through and finding all the solutions for every n. And we're going to sum that up. And then we're going to multiply by something. So I multiply by q to the n. So basically, the number that I was interested in is now the coefficient in front of q to the n in this infinite sum. And roughly speaking, the idea is this. It's this simple idea. If you change these numbers, if you change these s's, then the function will behave differently, right? So just think of a simple example. Suppose these numbers were like 2 to the n. So if these numbers are basically 2 to the n or exactly 2 to the n, then you can ask the question, for which choices of q does this sum converge? And if this was 2 to the n, then because the sum would be exploding if q was not very small, because here we have, if q is bigger than 1, for example, of course it would be blowing up. We'd have 2 to the n there. So the q has to be smaller than 1 over 2 to the n to get the convergence. And indeed you can show, for instance, the q has to be less than a half, so that q to the n is less than 1 over 2 to the n. So you'd get that this converges for q less than a half in that case. And the relationship between the tau here, which is in the complex upper half plane, and q is that q is e to the 2 pi I tau. So tau has a real and imaginary part, and the real part So e to the 2 pi I times a real number is a rotation around a circle. But the imaginary part gives us the absolute value of q, right? So the absolute value of q will be e to the minus 2 pi times the imaginary part of tau, which we often write as v. So in the example that I just gave, you would need to have q in absolute value less than a half, and then you'd figure out that the imaginary part is restricted in some way to get convergence. And we're going to do this with both of these functions, theta and theta star, with the s and the s star. And from complex analysis, if you take one of these functions and you multiply by q to the minus n minus 1, and you integrate in some path around 0 inside the radius of convergence, so these numbers in our case will be polynomial in n. You can easily check that the number of solutions of a sum of squares. So for instance, if you have the sum of xj squared or yj squared, if this sum equals n and all the aj's are non-negative, I'm only allowing aj to be positive actually, because these are repeated, the number of repeats, they're positive integers. So this sum, if the yj is bigger than the square root of n, this will already be too big just in the single term, and every term is non-negative, so you know that that can't happen. So each of the yj's is obviously bounded by the square root of n. And so the number of solutions is bounded by n to the L divided by 2 just by this simple combinatorial argument. And so we know that these numbers do not grow too fast, so actually if absolute value of q is less than 1, then we will get exponential decay from the q to the n, and that will make it converge. So what we want is anything inside a path of radius less than 1, so anything inside the unit circle, the unit ball of radius 1, any path around 0. Then if you take a path inside the complex upper half plane around in some way like this, and you go around one time in a simple path, then you get the residue of everything inside the region that you surrounded. And in this case, because these functions, you can check that they converge everywhere because of the decay that I just described. So they don't blow up anywhere. They're complex analytic and they don't blow up anywhere. So this function only blows up when the q to the minus n minus 1 blows up. But that only happens for q equals 0. So the only place there could be a residue is at q equals 0. And the residue from this expansion, we know that the residue is exactly this number here. And so that's why you get this formula. And now the basic idea is to take that integral. So now we have the number we want to compute as some integral, and you want to take the integral and split it up into a bunch of pieces. So you split it up in a bunch of pieces, and you'll try to compute the different pieces explicitly or approximate them. This is the essential idea. So you can take a small arc near the absolute value equal to 1, so near the edge of the circle. And if this function happens to grow near that number in that little arc, if it grows when you get to that rational number, then this arc will give a large contribution. And if it doesn't grow, then it won't give a very large contribution. So this is one way to sort of interpret the idea here. And if it decays, of course, it won't give any or very, very, very little contribution as you get further and further out closer to the edge. So here's an example, which was the original example of this method, which is called the circle method. So it's called a circle because the first path that they took was indeed a circle. They integrated around a circle of the partition function. So what's the partition function? Well, it's P of n is the number of ways to write a sum, to sum up to n. So for example, P of 5 is 7. because we have 5 is 4 plus 1 is 3 plus 2 is 3 plus 1 plus 1 is 2 plus 2 plus 1 is 2 plus 1 plus 1 plus 1 is equal to 1 plus 1 plus 1 plus 1. So you may have heard of the partition function. And there's a question, so P of 5 is 7, and if you look at P of 200, it's about 4 billion. And so there was a question of how quickly these numbers grew, and if you could find a formula for these. And what Hardy and Ramanujan did was they took these numbers and they looked at the generating function. And they then did this integral just as I wrote in the previous page. And in order to figure out how they grew as you get closer to the edge, they used the fact that this function is a nice function. So it's what we call a modular form. Now, I'll briefly explain what a modular form is, but basically what you want to think about is that it's smooth, so in this case holomorphic, and it has a lot of symmetries. So in other words, for different values of tau, or equivalently for different values of q, the values are related so that they may not be equal. It's not exactly that they're the same value at different points, but they're related to each other. And so that's the property that's important here, because if you have them related to each other, then you only have to figure out some of the values because it tells you all of the other values as well. And so this kind of relates different rational numbers to each other, different h over k near the edge, right? The edge is sort of when you get to absolute value equal to 1, which is the same as e to the 2 pi I times that rational number. And so the tau is like h over k, and the q is like this. And if you know the growth towards h over k, then to get that, you use a relationship between h over k and infinity, because infinity, so if you take infinity, it maps to q equals 0, because e to the 2 pi I tau, if you take I infinity, you get e to the minus 2 pi infinity, which is a 0. I mean, it's the limit, of course, of e to the minus 2 pi r, and r goes to 0. Okay, so the good news is that this theta function with the star, it's counting the number of solutions, is a modular form. But the one without the star, the one that we're interested in for this talk, is not a modular form. And so essentially the goal of this talk is to relate the non-modular form with the modular form. And then once you do that, you can use a lot of well-known techniques in the theory of modular forms to understand this object up to an error term. Of course, there was an error in the theorem, right? There's some kind of error between the two, but you can get some information about this from the information about that, and you get the information about that from the fact that it's a modular form. So what is a modular form? I've said the word multiple times now. So a modular form of integral weight, it satisfies what we call modularity. These are the symmetries I was talking about. So if you take f of gamma z, which is just az plus b divided by cz plus d, so fractional linear transformations, which you can think of if you take the matrix A, B, C, D, and you multiply by a vector z1, which you can think of as z over 1, then this would just be multiplication of matrices when we divide z divided by 1, and then we take az plus b and cz plus d, and this is what we call projective space, where we take the ratio of them. And so these fractional linear transformations that you may have learned about in complex analysis are really just multiplication of matrices. And then we apply some homomorphicity properties. So the relationship here, this is just a definition of this operator called a slash operator. And this is the property that it has, is that it's equal to f. When I multiply by the cz plus d to the minus k, and I take f of gamma z, then I get f back. So that's the symmetry. If I take f of az plus b over cz plus d, I get this factor times f of z. Sorry, this should be f of z. And it's holomorphic, and it's bounded has bounded growth towards the cusp. So in other words, as I go towards h over k, it grows in a certain way that's sort of controlled. It can be explicitly written down, but let me just say that it has some kind of explicit growth towards that cusp. Here's an example, something called the Eisenstein series. Now what you do is you take a function, so this is what is commonly called a Poincare series. You take some function, we call it a test function, and what you do is you simply slash it with all the matrices and then you add them up. And because we slashed with all of the matrices, we sort of added in all the symmetries that we wanted. And if you take the simplest function, that's the constant function, then this slash, remember in my definition, always had this extra term cz plus d to the minus k. And then I multiply times the function evaluated at different points. But of course, the constant function 1 at any point is always 1. So that just gives exactly the cz plus d to the minus k factor. And there's a condition that the C and D have to be relatively prime. And that happens because otherwise, so this is, the gamma is going to be A, B, C, D, and the C and D have to be relatively prime because otherwise the determinant cannot be 1. It can't be an element of SL2Z. The determinant needs to be 1. And so this is, as I said, weight K by construction, essentially because you have all the symmetries and then you slash with another matrix, another 2x2 SLTZ matrix. It turns out that slashing by one matrix and then another is the same as slashing with the product. And so you end up getting exactly that it's the same as slashing with this, but then you just change gamma to gamma naught inverse, and the gamma naught inverse disappears, and then you just get the original function back. And so this thing is equal to EK. And essentially, it also takes in some of the properties of the function 1. And of course, you have to be careful with convergence. So actually, you need K to be bigger than 2 for this to all happen, because when I did this, I did a change of variables right here, right? So to go from this step to this step, I made a change of variables with my gammas. But that means I reordered the sum. And whenever I reorder the sum, I have to make sure the convergence is absolute and locally uniform to allow for that to occur, or that it satisfies any conditions that imply that it's convergent in the right way. But we need some kind of convergence for that to happen. Nice convergence. Okay, so I'm going to look at a more general object now called a quantum modular form. So a quantum modular form, so if it was a modular form, then when I take f and I subtract f slashed with gamma, if it's a modular form, that should be 0, right? These should be equal if it's a modular form. So Zagier defined something called a quantum modular form to be that the difference is not 0, but simpler in some reasonable sense. And there's some conditions like it has to be holomorphic or at least real analytic, some kind of smoothness conditions, and again, some growth conditions at when you go towards rational numbers. These thetas, the ones we're interested in, where we allow the non-negative parameters, are what we call partial theta functions. And they're partial exactly because we're taking one portion of the lattice, right? We take a big lattice and we only look at those ones in one quadrant. And so they're partial in that they're half. There's also something called a false theta function, where what you do is you take the same kind of thing, but you now take everything, but instead of taking one quadrant, you count the opposite quadrant by a negative sign. So you take both quadrants, but you don't count them both positively. You count one positively and one negatively. And so they don't come to the same thing. Now, of course, if I take the regular theta function, it would just be, so this is in one variable, I should say. So this is the one variable version of what we're looking at. I can also take the one variable version of the theta function. And if I take these partial theta functions, so if I add these up together, if nu is positive, then I just get 2. But if nu is negative, then when I add them up, I get 0. So the theta R2m alpha is exactly the ones where we have nu positive, and so we get exactly 1/2 of the sum. And then we take all those together because this is just one variable. So we take the product of each of those. But the one with the star is just the product of these ones with the full lattice and no problem with the signs. Okay. Now, the starting point of our project was a result of Katrin Brinkmans with Nazaroglu, who was a postdoc of hers at the time, I believe. And essentially what they showed are that these false theta functions, although they're not modular forms, they're vector valued quantum modular forms. So they behave like modular forms in some sense, in the sense that there's some error to when you take the difference, but the error is simpler in this sense. And the error, when I take the function minus the function slashed, what I get is I get a certain integral of a simpler function. And the simpler function is just the one variable theta function, but now there's a parameter in here, which is the nu. So I'm summing over all the nus in this congruence class over the integers now, so the whole one, but I'm multiplying by nu. And these are actually modular forms of weight 3/2. So these are modular forms of a certain type. So in that sense, these are simpler. We understand them better. Now, what do I mean by vector valued? Well, what I mean by that is we take a bunch of f's, f1, f2, and so on and so forth. And when we slash, we get a linear combination of the original function back. And it has the other conditions like we wanted before. And we actually want vector valued in half integral weight. So I have to say there's some sort of extra parameter here, which is called a multiplier system. We won't worry too much about that. There's some consistency conditions and the absolute value is 1. But basically it needs to be there. And the reason is because if k is a half integer, if you remember from complex analysis, if k is a half integer, the square root is not a holomorphic function. So there are 2 choices for the square root. And it might be that for different choices of gamma, you choose different choices of the square root, and it may not be consistent. So in some sense, this nu of gamma fixes the square root problem, let's say. This is one way to think about it. Okay, so what Brinkman and Nazaroglu actually showed was that the f slashed in a weight 1/2, so it's like a half integral weight modular form of weight 1/2. It's equal to a linear combination of other ones of the same type. So other false theta functions plus that integral that I mentioned earlier, what I called the error to modularity. So altogether, we have something that almost is like a vector valued modular form. If it was just the first line, it would be what we call a vector valued modular form. And indeed, if I take the theta function, the standard one, I do get this kind of identity. And actually the C's are the same. So really that they're behaving almost exactly the same, but there's this error that comes from this integral. So up to that error to modularity, these really look like the same thing. So it seems reasonable that we should be able to relate them back together, to relate them to each other. Okay, so as I mentioned at the beginning with the circle method, the whole point is that we want to know the growth as you get towards these rational numbers, h over k. because then that will tell us what contribution you get from the arc that's near that rational number. So how do we get the growth from these relationships that we've written up here? And I should say that these gammas can be anything in SL2Z. So actually it works for every element of SL2Z. So every rational number is equivalent to infinity under SL2Z. So we can send anything to infinity. And the price we pay is that we don't get the original function back, but some linear combination of the other functions and this other integral. So since every rational number is equivalent by fractional linear transformations to infinity, we can take a matrix that sends infinity to that rational number, or vice versa. So we can pick such a matrix, and then m tau will approach h over k as tau goes to I infinity, right? Because this point gets sent to h over k. So if my tau is approaching that point, then m tau will also approach h over k. But now I can use the modularity on the previous page, and the right-hand side here, I know how this behaves because now tau is going to infinity, right? So this one is going, the parameter is going to h over k, but this one, the parameter is going to infinity. So the growth here, as I get close to h over k, is determined by the growth here as tau gets to infinity. And so I've moved the question from a question about some rational number, and the problem is that these expansions that we're taking with Q, they don't converge when I get to absolute value 1, right? We know that diverges as we get there, or at least it doesn't obviously absolutely converge. But near 0, these converge near Q equals 0, these converge very, very well. So we moved the problem from something that we don't understand very well, near the edge of this circle, to the middle of the circle where we understand things very, very well. And that is how the modularity is used. And as tau goes to infinity, you just get the constant term of that expansion because the Q is going to 0 and you're taking positive powers of Q, those all disappear, and then they have the Q to the 0. So we start at Q to the 0, then Q the first, then Q the second, and so on and so forth. And actually the F even vanishes there because we have nu of 0. That's a sign of 0, I mean, and that vanishes. So even for the false theta function, we don't get any contribution. We do get a contribution sometimes for some choices of L here. And then all that remains is to understand the growth of this integral that we're looking at. To do that, you basically do a very careful integration by parts calculation. It's something like 10 or 15 pages of calculations. So I'm not going to go into any details there, but you do some very careful integration by parts. And the conclusion is that the error to modularity grows slightly slower than a constant term. So the function 1 grows a little bit faster than this integral that we're looking at as you approach infinity. And specifically, as m tau is h over k plus iz over k, as z goes to 0, so as z goes to 0, this will approach h over k. Basically, this grows, or decays rather, like the square root of z. So we get an extra square root of z, and z is going to 0. And so we get some extra help, some vanishing from these things. And that's why we expect them to give a smaller contribution than the main term. And that's why we expect the values to be about the same. So basically, as we approach the edge of the circle, this integral part is contributing less to the integral along the arc than the constant term 1. And so it's smaller than the theta function, which contributes 1. Okay, so if I just write down what my theta star and my theta are in terms of these one variable things, so the theta function that's modular form and the false theta function, then I can write out this product, and the first thing I do is I multiply all these together, right? I multiply all of the theta RMs together, but I have this 1/2 here, so I get 1/2 to the L times the theta with the star. But that's exactly what I expected, right? I want to say that this one is approximately that one. So that's the same as saying that each of these ones, the other ones that come from the product, is small. And this sum is just the sum over all the possible choices, all the subsets of 1 up to L, but you don't take everything. So the things that are in the set, you take the theta, the var theta, and you take the false theta function for the things that are not in the set. And we can't take the full set because this one is the full set. So I split that one off separately because I expect it to be large, and also because I wanted to show that when I multiply all these pieces together, I get exactly what I'm expecting, this 1/2 to the L times that, the theta with the star. And then you expand everything around the cusps, you look at the growth, and the hardest part is the ones where you have to multiply the error to modularity times constant terms. Other terms decay very, very fast. They decay exponentially, right? If I take q to the first power, then it's decaying exponentially as q goes to 0. Well, sorry, it's decaying exponentially in tau. It's decaying linearly in q as q goes to 0. But this error to modularity, this integral, decays not as fast as q. It decays like the log of q, or log of 1 plus absolute value of q, something like that. Okay, so you just have to show that these terms contribute less to the original integral in the circle method. So as I said, the false theta functions actually vanish towards infinity because they have the sign of nu in there. So the constant term vanishes for those ones. So those ones don't have a constant term. So you just have the contribution from the constant terms of these var thetas, and also from the errors of modularity, error to modularity. Okay, so if you do all that, you basically get the theorem that I wrote down, that the main terms are the same with up to this error, and the error turns out to be n to the 15/16 plus epsilon. Again, I said it's a long calculation. Now for the main term, and by the main term I essentially mean the thing coming from the original theta star, right? So now we've reduced the problem to looking at that one, and now we want to study the number of solutions to this original question. And as I said, it's a modular form, so we can use some techniques now that we know. The original method that was used was, again, the circle method. And this was done by Kloosterman. And there's a few more details to compute the main part, but essentially you rewrite so that you get an entire integral in some way, and you get a residue of something. And this becomes what's called the singular series, which is the main term. And then there's some pieces that had to be added in or subtracted to get the circle the way they wanted, so that you get this main term, and then you have to bound everything else as an error term. And if you do that, you get the same error term that we got, n to the 15/16. But actually, you can use the fact that theta star is a modular form, and modular forms have a nice way that they decompose into the Eisenstein series, like I introduced before. Remember, I gave an example of an Eisenstein series, and something called a cusp form, which vanishes towards all these rational numbers. So we can think of it as small in the sense that since it vanishes towards all these rational numbers, it shouldn't give as much of a contribution to the coefficients from the circle method. From our understanding of the circle method as we've described it, if it vanishes towards all these rational numbers, then the integral around the circle will not give as much of a contribution as the Eisenstein series, which has a constant term at some of those numbers. And the Eisenstein series, happily, has coefficients that are like sum of divisors. So they have very nice, like the sum of all divisors d dividing n of d. And the function g has small coefficients. And actually, there was something called the Weil conjectures that were proven by Deligne that show that in the integral weight case that we're looking at, so this is weight 2, that these coefficients grow smaller than n to the 1/2 plus epsilon. And it's actually even more precise what he proved. But the point is that if you take the sum of divisors, d dividing n, and you sum up all of those, obviously that's bigger than n, because n is one of the divisors. So this is basically linear. Now, it's a little more complicated than that, but that's essentially the idea. And this one is like square root of n at most. So this one is an error term in comparison to the Eisenstein series. So the main contribution should be from here. Okay, there's yet another interpretation of this main term. If I take something from the theory of quadratic forms, so a quadratic form is just a function in n variables that is homogeneous of degree 2. So that means that if I multiply all the variables by a fixed number r squared will pull out. So if I multiply everything by r, then r pulls out of everything. It's homogeneous of degree 2, so an r squared will pull out. And if you do sort of a change of variables, something called an isometry, I won't go into too much detail, essentially in the sense of the lattice. Remember I described the lattice way of looking at these things. The distance, if it's preserved, you think of that as a rotation, or what we call an isometry. And you have that two things are the same if they're just a change of variables from one to the other. So if they're just, the points are just moved around, right? So if I take just an Euclidean space and I spin a lattice, it's really the same lattice. I'm just looking at it from a different perspective. And so, for instance, x plus y squared is the same as x squared plus y squared, because all I did was I made a change of variables. X goes to x plus y. And you can do the same thing over the p-adic numbers. Again, I don't want to go into too much detail, but if you do this, there's some kind of equivalence relation that if something's equivalent for every prime p, then we say it's in the same genus. And we again form the theta functions, just as I've done previously for the sum of squares. And it's again a modular form. Lagrange's four squares theorem that I mentioned at the beginning is actually an easy consequence of the fact that the space that this object is in is a one-dimensional vector space. So if it's a one-dimensional vector space and we have another element in the space, they must be proportional to each other. And this actually gives you a formula for the number of ways to write the sum of four squares equals n. Because the other one, we have an explicit formula for it. It's one of these sums of divisors things that I mentioned here. It's one of these Eisenstein series. So these ones, we know what the numbers look like. So if we can relate them together, then we actually get an identity. And that's kind of part of the idea of what we're going to try to do with this now that we have this relationship. And it turns out that if I take some weighted average of everything in the genus, so I weight by the number of automorphs, which is really just the number of ways you can rotate it to itself. So like if I take x squared plus y squared, I can rotate by taking x to minus x, and I get the same thing. The lattice doesn't change. So the number of rotations that send the lattice to itself is these automorphs. And so I take a weighted average where I divide by the number of automorphs. So you can think of it as like it's multi-counted, right? Because the same thing shows up multiple times. X and minus x are sort of matching. There's a symmetry. So we divide out the symmetry so we want kind of distinct solutions in some sense. And if you do that, it turns out that this theta genus that comes from taking the sums of these, it actually is the Eisenstein series component. And it can also be computed another way as a product of what are called local densities from the algebraic side of things. So these are also computed a totally different way using algebraic theory. So this is what I'm describing as an analytic description, but you can also use algebraic techniques to understand these kind of averages. And so the Eisenstein series can be computed in multiple different ways, But what it boils down to is that it's some sum of divisors. So there's some set, let's say SRM alpha, so some particular set, like maybe all the divisors that are not divisible by 4, something like that, or all the divisors that are 7 mod 8, something like that. So you take only the divisors that satisfy the certain condition and you sum them up. And then you have this error from the cusp part, which is just by Deligne's work, n to the 1/2 plus epsilon. So we have some sum of divisors plus a square root of n error. And Kloosterman's error was, he has the same main term written a different way. As I said, he writes it as these what are called singular series, but his error is n to the 15/16 plus epsilon, which is not a surprise because it was much, much earlier, and the result of Deligne was really groundbreaking. It was already conjectured previously by Weil. So from our theorem, using either of these identities, we get that the one, sorry, this should be the one without the star. Yeah, sorry, this should be the one without the star is equal to the sum with the star plus O of n to the 15/16 plus epsilon. But then the one with the star is this sum of divisors plus O of, say, square root of n times n to the epsilon, a little bit worse than square root of n. And so overall, we get a formula for the number of solutions is some sum of divisors plus an error term, where the error is smaller than this sum of divisors. And so we get sort of a main contribution, unless this is empty. Obviously, if it's empty, then it doesn't happen. And that does happen sometimes because, for instance, if you take just x squared, it can't represent every number. So some of these are going to be 0, right? So we have to have sometimes there's some congruence conditions. So if I take 2x squared plus 2y squared, I obviously can't get any odd numbers, that kind of thing. And so there's some conditions that might happen that might exclude some numbers, in which case, in those cases, it'll be empty. So let's do a couple of examples where we know what this S star is essentially already. And if you do the examples where we know this, you get a formula. If I take hexagonal numbers, hexagonal plus hexagonal plus hexagonal plus twice hexagonal, and I find out how many ways to sum up to n, this will be -1/64 times the sum of all divisors of 8n plus 5 of 8/d times d. So this is the Legendre symbol or the Kronecker symbol. In this case, it can be considered the Jacobi Legendre symbol because d must be odd. All the divisors are odd. Up to an error, we get exactly this sum. And then for an individual n, you can compute this. So for instance, you can take the ratio of these and you'll see that it should be small. When the difference between them, and I divide by powers of n, it should be small. And then if I take, for instance, pentagonal numbers, I take sum of 4 pentagonal numbers, I get 1/24 times the sum d dividing 6n plus 1 of d, plus again, the same type of error. And these right-hand sides, I should say, in this case, actually, this is exactly the number of solutions for the hexagonal numbers, I believe. And this is exactly, I think this one's not exactly the number of solutions, but it might be, I'm not sure. So we get these nice formulas up to some error term. And so that's one of the things that you get from this kind of analysis. So this is all that I wanted to share today. I hope that you found it interesting. And if there's any questions, I'd love to answer them. Thanks a lot. Oh, I think you're muted right now. Or yeah. Okay.
Is it okay now, Ben?
I hear you now. Yeah.
Yeah. So thank you so much, Ben. It's a wonderful talk of relating some very basic questions with the theory of modular forms, mock modular forms, etc. So now, if there are any questions, people can ask. Yeah. So Krishna has a question. Then we'll go back to the YouTube questions and all. So I give it to Krishna.
Okay.
Hi, Ben.
Hi.
So, is there any way we can improve the error term? Like 15/16 doesn't seem like a lot of saving. So,
yeah, probably. We didn't we didn't try very hard to improve the error term. I'm curious how much one can get out of that. Now, obviously, so what we're using at one step is something called Kloosterman's fundamental lemma. So we're actually using bounds by Kloosterman. At the time, all he knew was the fact that it decays towards the cusps, the cusp part, basically. And using that information and the circle method, you get this kind of error. Now, obviously, Deligne did a lot better for the same functions that Kloosterman was looking at. So there might be a method that gives a better error term, but because we don't have the direct connection with modular forms, it doesn't immediately follow from Deligne's work. So perhaps one can make improvements in the circle method or try to attack it from a different perspective using the fact that it's a quantum modular form. And then you might be able to do so, but it's not immediately obvious that what this gives you in the end. So it probably some work on the analysis side, on the circle method side, like maybe looking for some recent improvements in the circle method since Kloosterman's time, and just cancellation of sums of Kloosterman sums might improve the error term. Actually, we were just trying to get it smaller than the main term, but so we didn't worry too much about that. But I think it probably is possible to make it smaller.
Okay. Is there any value that you would like to conjecture right now?
Yeah, I mean, I'm not sure. I would not be too surprised if it's also square root of n.
Even that's what I also thought. Like.
Yeah, I mean, I wouldn't be too surprised, or n to the 1/2 plus epsilon. So I think, yeah, I what I kind of think is the following, and so I have a reason beyond just the fact that you get Deligne's result. So when we got the improvement of the square root of z in the, so the error term, instead of being like a constant, it grows like square root of z, and z is going to 0. So we're getting savings of a square root of z.
Okay.
If you do 3 variables, so for every variable that you get, you actually have to divide by a square root of z. So you could interpret this as canceling one of the dimensions, maybe. If you could turn that into a real argument somehow, then maybe you can say that it grows the same as the solution in 3 variables.
Okay.
And that grows with an upper bound of square root of n. So there's some reason to believe that if you take constant term times an error to modularity, the integral term, that term should be the same as like a 3 variable one instead. That's what I suspect.
Okay. And
but yeah, go ahead.
So, is there an L function side to this whole problem? Because you were actually talking about modular forms, and if you take the L function associated to that modular forms, can we assume, I know, maybe something like a GRH and try to improve the error estimate or something like that?
Yeah. So
the averages.
Yeah. So let me start by saying that so first of all, it depends on your definition of L function. So if you want, so when you say modular form, a lot of people think of Hecke eigenform or new form.
Yeah. Okay. Yeah.
This is not that. This is some linear combination of many different Hecke eigenforms. So it's in the space spanned by those things, but it's not itself that. So the L function, you could define an L function, but it won't be. It will have some of the properties. It will have the functional equation, but it won't have the Euler product because the coefficients are not multiplicative.
Okay.
So it will have some of the things you want. And indeed, you might be able to study some things from the L function side, but then you have to translate the fact that you're taking some linear combination of those things. And so it's not clear exactly how it translates back.
Okay. Okay. Thank you. Thanks so much.
Yeah. Yeah.
So any more questions from YouTube channel? No, it's not there. Okay, so I have just a quick question, Ben. So these questions, like these problems, how about in case of any, let's say, an imaginary quadratic field in the ring of integers?
Yeah.
Like,
So like you replace the integers with an imaginary quadratic is what you're saying.
yes. So it's the similar kind of questions. Like we have seen that the sums of squares and all other questions are being translated.
Yeah, one could also consider these questions. I mean, I guess probably you first have to restrict because in the imaginary quadratic, you don't represent everything. Like that's known in general. But if you restrict to the numbers that are represented by that form with the full lattice, I would expect that if you take a partial lattice like this, it probably should be somewhat uniformly distributed in this way. I mean, essentially that's what we're checking, right? We're saying like, if I take a lattice and I take only part of the lattice, it should be like the portion of the lattice that I take, it should be that many representations. So basically in each of the portions of the lattice, it's the same. And if your lattice is over Z, then this is what we did. But if the lattice is over something else, I would expect it to be probably similar. But that doesn't, I mean, that may or may not be true, but I would sort of expect it, I guess.
It's not been explored yet. That's
not that I know of, no.
Yeah, so if there are no more questions, let's thank Ben once more for this wonderful talk. And thank you so much, Ben. See you soon sometime.
Yeah, hopefully soon.